So let's look at this diagram. In the diagram, a person fires a gun horizontally and exactly the same time drops a bullet from the hand pulling the trigger. Ignore air resistance. Is there any difference in the time between the two bullets hitting the ground? So basically, you have one bullet that he just dropped from the gun. Oh, sorry. So he dropped a bullet from the gun, and at the same time he fires a bullet, right? Is there time difference between the two bullets hitting the ground? No, because they're independent, right? So if you push that bullet forward, it's still going to drop to the ground eventually, right? It's just that you're going to travel very far. That's why I use the gun example, because it's firing so fast that you thought you never go down. In fact, it does go down. At the same time, you drop a bullet. So it goes very fast. Okay, so no, because the two components, the vertical component and horizontal component of velocity are independent. So by traveling forward very fast does not affect how fast you fall down. Yes? That's what that means. So there is no difference. Okay, good. And then we'll do next problem. Have a think. It's a multiple choice. There's 5 options, and you choose one option. Okay, snowmobile. Suppose a snowmobile is equipped with a flare launcher, which is capable of launching a flare vertically, right? So you have a, I don't know, so maybe a car, and then you just launch something up in the air. If the snowmobile is in motion or a horizontal plane and launches the flare and maintains a constant velocity after the launch, so it's traveling forward at the same time, you launch a flare as well, where would the flare land after it falls down, right? Would it land in front of the mobile, behind, in the mobile, or it depends on the velocity, or none of the above? Which one would you choose and why? You say C. Who else wants C? And why? It's the same comment as above. Horizontal component doesn't affect your vertical component. So as you move forward, what happened to the flare? It moves forward as well. And by the time you reach here, you will fall back to the car, right? I've got a video. A professor from the university did the experiment. Let's watch this. Okay, so watch. He's shooting that thing up, goes back down, right? And then what he does is he's going to push forward. Okay, so he's going to push this forward. Okay, all right, watch this. So it's going to move the machine forward. At a constant speed. Taking a long time. Okay, so you're going to push forward, and at this point, it will trigger the ball to go up, and then see if it lands back into the car. Yep, come in. Okay, watch this. There should be volumes. All right. Can't hear. Anyway. All right. Watch. Goes back, right? And see, goes back, right? So it just goes up and goes back, because the ball and the car is traveling at the same speed, right? So as you shoot it up, it goes back to the car, right? As you go forward. Yes? Okay, good. All right, so we learned these things, and then let's move on to do some HSC questions. Okay, let's look at the first question. All right, this is from 2005 HSC. Have a look. An experimental rocket is at a height of 5,000 meters. ascending with a velocity of this at an angle of 45 degrees when the engine stops. It's important they say the engine stops, that's when it's a projectile, okay? So it's at an angle of 45 degrees, yes? And the speed is 200 root 2. Okay, all right. So this is what happened, and then we'll go after the time. The equation of motion of the rocket is this. It's given to you. So normally in the HSC question, in exam question, they don't ask you to derive it because it's quite easy to do that. Sometimes they ask you to derive it, but most of the time they just give it to you. They want you to answer question using this equation. Okay, so T is measured in seconds after the engine stops. Do not show this, so you just have to use this equation. Now, it asks you to find out what is the maximum height the rocket will reach when it reach, and when will it reach this height. Okay, how do I find maximum height? That's when we do. What do we do to find maximum height? Yes, y dot 0. Remember, maximum height, y dot 0. It stops rising. Okay, let's do that. That will help you to find the time it takes to get to the maximum height. Okay, let's enlarge this. Okay, let's write down y dot. So y dot equals to negative 9.8 t plus 200. And how do I find the time? You make that equal to 0 using some calculation. You'll get 200 over 9.8. And then just use your calculator. 200 divided by 9.8. That gives you 20.4, about 20.4 seconds. Okay. Okay, so that's the time it takes to reach the maximum height. And what is the maximum height? That's when you have to substitute this into y. Y equals to negative 4.9 t squared. Now, I will substitute the exact value. 200 over 9.8. Rather than 20.45 to keep it exact, plus 200 times 200 over 9.8 and plus 5,000, and use your calculator. To help you to do that, maybe you can save it onto the answers. Negative 4.9 answer square plus 200 times answer plus 5,000. Perfect. 7,040.81 meters. That's how high it rises up in the air. So it's pretty easy, and this question is worth 2 marks. See that little square bracket? 2 means 2 marks. So 1 mark for getting the correct time, 1 mark for getting the correct maximum height. All right, good. Okay, now we're going to continue to do the question. We're going to refer to the diagram. So we're going to work out the answer the next part of the question. Okay, so the next part says the pilot can only operate the ejection seat when the rocket is descending at an angle between 45 degrees and 60 degrees to the horizontal. What are the earliest and the latest time the pilot can operate the ejection seat? Okay, so if you look at this, it has to descend between 45 degrees and 60 degrees. So if we draw this, it must be sometime here when the angle is 45, or the latest will be, as you go down, you will see the angle will increase to 60. So that's the earliest you can eject, and that's the latest, right? So what do? We have to find the time. There's T1, T2. We need to find both of these times. Okay, how do I find this? Now, what's the formula that calculates the angle? How do I find angle? How do you find angles? What's the formula? It's tan theta equal y dot over x dot. Yes? Use that formula to find angle. And we've got formula for y dot and x dot. Let's do that. So so what's y dot equal to? Y dot equals to negative 9.8 t plus 200. X dot equals to 200. Okay? So you want to find what time so that the angle is 45 degrees. Now remember, it's descending, therefore the angle must be negative. So you substitute negative 45, then you give you negative equals tan negative 45 equals to negative 9.8t plus 200 over 200. And you solve this equation for time. Okay, so what do we do? Yes, we're going to continue. So tan negative 45 is negative 1. So you get negative 1 equals to 200 t plus 200. And then move this 200 to the other side. Like that. And solve for t. So t will be 9.8t equal to 400. T equal to 400 over 9.8. And then use your... So the earliest time you can eject must be 400 divided by 9.8. So the earliest time you can eject is about 40.8 seconds. Okay, that's the earliest time you can eject. And you do the same thing to find the latest time you can eject using 60 degree. Okay, have a try. I want you to have a try and the same thing. Okay, have a try. So do it with the 60 degrees. Remember to put negative 60 so you get a negative angle. Otherwise, you will not get the same correct answer for time. Okay. So it's 3 marks this question. So 1 mark for this time, 1 mark for the other time, and maybe 1 mark if you know this formula. Okay, good. All right, so do the other one, tan negative 60. Have a try. Okay, so tan negative 60. Negative 60 equal to y dot over x dot. And negative 60 is negative root 3. So it times by 200. And then I will leave the detail working to for yourself. So you will get something like this. 200, 1 plus root 3 over 9.8. Okay, I skipped some working. Ran out of space. So 200 times 1 plus root 3. First bracket divided by 9.8. So the latest time you can eject is about 55.8 seconds. 55.8 seconds. All right, good. All right, any question? And then we'll go one more part. All right, good. Last part. What do? We also have to open safely, so the pilot must eject when the speed is no more than 350 meters per second. What's the latest time the pilot can eject safely? Okay, so what's the formula for speed? V equal, what's V equal to? X dot square plus Y dot square, right? Square root, or without the square root. Oops. Okay, now square equal to x dot square plus y dot square. So what you do is, so you're going to write 350 square equals to x dot square plus y dot square negative 9.8t plus 200. 200 t. Okay, good. Right. Okay. Okay, good. Now the question is, you're going to find time. How do you solve this equation? How do you solve this equation? Any suggestion? Quadratic, so what do we do? Expand, yep. And then expand, simplify, and then you get something t squared something. Okay. And then after you expand, you may have to use the quadratic formula and then work out, right? That's very long. There's a faster way. You still have to solve a quadratic, but you can do it much quicker. The reason why is this is a perfect square. It's already a perfect square, so what do? You keep it as a perfect square, right? So you go 350 square minus 200 square equal to this. So you work out on a calculator, you do 350 square minus 200 square equal 82500. 82500. Just 30 20. And then what you do next is you're going to square root the answer, right? Right, so you're going to square root plus or minus. Okay, let's do that. So if I square root it, does it give me exact answer? Doesn't. So keep it in square root form. So what you do is keep it like this, and then to find this thing, you get 9.8t equals to 200 plus or minus this thing. And of course, t is positive. So 200 plus or minus that. Okay, and then you use your calculator. So when you do that, make sure you do 200. So you do a fraction, 200 minus root 82500 over 9.8, which you get negative, so you do the positive one, plus, so 49.7. So the latest time you can eject is 49.7 seconds. So this is quite an interesting problem where it involves most of the formulas you learn about projectile and then put them into context in this problem. So you should study this problem again. So probably 1 mark if you know to do this, 1 mark if you got the correct time. Okay, good. All right, that's one of the HSC questions. We're going to do more HSC questions. All right. Okay, next problem, 2009, question 1. Question 6. All right, all finished? Okay, next page, 2009, question 6. Okay, in this problem, there are 2 projectiles being fired towards each other. So you have x1, y1, x2, y2. So one's being projected this way, one's projected this way. So somewhere they will meet, right? So one's fired this way, one fired the other way. So they will want them to collide. So 2 points A and B on the cliff, one on the cliff top, one on the other side of the deep valley. Let H and R be the vertical horizontal distance between them. The angle theta is this. Okay, so at time 0, these are the equation of motion. The equation for this one is this. The equation for the one that going downward is this, right? Okay, so do not prove this equation. It's given to you. You have to find the time at which the 2 x values are equal. Okay, all right, so how do we do this? We have to, so they already tell you what to do. That's only 1 mark, so not a lot to do. So you just have to make these 2 equal to each other. Actually, no, these 2. So make x1 equal to x2. Let's make it a bit bigger. So x1 equal to ut cos theta equal to r minus vt cos theta. So what you have to do is to make t the subject. And Therefore, they change the little t to a capital T, because at the capital T, the two particles will meet, right? Okay, with the time at which the two x values are equal. So we have to make capital T the subject. So you just have to move this term to the left side and write down u capital T cos theta plus vt cos theta equal to r, right? Factorize the t cos theta out, u plus v, and to find capital T, you go r over u plus v over cos theta. Yeah, so it's pretty easy. All right, have a think. And then we'll have to show the two particles collide. Okay, so how do we show they collide? Okay, all right, so we're going to show they collide each other. Okay, so if this is for 2 marks. So if they collide, then if the two particles collide, when t is equal to capital T, the x1 must equal to y2, right? So therefore, we can substitute, let me think. Actually, that's a harder way to do. What I'm going to do is, if they collide, then if the y values are equal, we show that the time at which they are equal is also t. I think that will be easier. So let's find the time when the y values are equal and show that this t equals to the other t. So, all right, let's do that. So y1 equal to y2. So if something collide, both the x and y value are the same. So let's make y1 equal to y2. So you write u2 ut sine theta minus half gt squared equal to h minus vt sine theta. Just copying the two equations they gave you. Right, the two will be equal, and then you will cancel the half gt squared. And then like before, let's find out the time. So we're going to move this term to the right side, left side. So you get ut sine theta plus vt sine theta equal to h. And factorize the t out, so t will be t sine theta u plus v equal to h. So therefore, t equal to h over u plus v sine theta. Alright, so it looks like they're different, but we actually have to show they're the same. They are the same, so we have to use some other information. So we've got the expression for the time when the two particles have the same height, y1 equal to y2. We have to show that at this time is exactly the same time when the two particles have the same x values. So now we have to use the shape that we saw from the diagram. See this diagram, h and r are related. So if I draw it over here, h, r are related. So what we could do is to change h in terms of r. Let's do that. So we can go h over r equal to tan theta. So h equal to r tan theta. Let's substitute that in here. So we get r tan theta over u plus v sine theta. Like that. But what's tan theta? Tan is sine over cos. And then the sine theta will cancel. So you end up getting r over u plus v cos theta, which is same as capital T. So at the same time, they will have the same y value and the x value, and then you conclude, therefore, the two particles will collide. Okay, done. Right, done. Okay, good. So now try to do the last part. Okay, so what do we do? So we got this. Okay, then we have one more part to go through. It says if the particle collide on the line x equal to lambda r, show that this is true. Okay, on the line x is lambda r. X lambda r will be this. It's a vertical line. Okay, this is x equal to lambda r. Okay, lambda's between 0 and 1. Okay, on this line. Okay, so what you do is this. Okay, so let's work out. So how do I prove this? So we use the fact that what to do. Lambda r. Okay, let's do this. Let's write down x1. The equation for x1 is this. So if they collide there, so basically x equal to lambda r, x equal to lambda r if the time they collide at this time, t equal to capital T, which is on the form u plus v over cos theta. So we substitute that into this equation, x equal to ut cos theta, and replace x by lambda r equal to u cos theta times r over u plus v cos theta. So substitute this into t, okay? And then you'll notice that the cos theta gets cancelled, and you just have to make v the subject. In fact, r gets cancelled as well. So you make v the subject. Okay, so let's try. So we end up getting lambda times u plus v equal to u. And then you expand lambda u plus lambda v equal to u. And then you make v the subject, so u minus lambda u. And then you factorize the u out. Actually, divide by lambda first. V equal to 1 over lambda u minus u. And you end up getting equals to, and you factorize the u out. So v equal to 1 over lambda minus 1. Let's write it again. 1 over lambda minus 1 u. Okay, we got it. Okay, have a think. So this is a harder topic, so have a look at so a lot of algebra involved in this topic. Okay, good, all done. Let's do the next problem. Okay, let's move on to do the next question when you're ready. All right, thank you. All right, let's move on. Okay, move on to the next. Next one is also a little bit harder. So a fire hose is at a ground level on horizontal plane. Water is projected from the base. The angle of projection theta, you're allowed to vary. The speed of the water as it leaves the hose, v meters per second, remains constant. You may assume that the origin is taken at the point of projection. The path of the water is given by these parametric equations. Okay, all right. So again, they give you these equations. So what you do is, so that's a projectile like this, water. So you have to prove that it reached the ground at this distance. So how do I do this? You have to find the time it reached the ground. That's when y is 0. So you do 0 equal to vt sine theta minus half gt squared. V sine theta. I'm going to let you write. Okay, good. So we got this. Let's find the time, factorize the t out. Sine theta. Okay, good. So what you do is you're going to write either time is 0 or the other time is when this is 0. So you write v sine theta minus half gt equal to 0. So you make t the subject, half gt equal to v sine theta, like that. And then t equal to gv, not gv, 2v sine theta over 2 over g. That's the timing when you reach the ground. To find how far you reach the ground, substitute that into x. X equal to v cos theta, t. Substitute this t value into x. And you write x equal to v cos theta. Okay, so if you do that, you end up getting v squared 2 sine theta cos theta over g, which is sine 2 theta, which is the same formula we derived before. Okay? So basically giving you the range of the particle, range of the water. Okay, good. So as you see, they will ask you to prove these formulas in the test, and that's 2 marks. So maybe 1 mark if you work out the time you reach there, 1 mark for showing it correctly. Okay, and this formula will be used later on in this question. Okay, so once you prove it, have a read the next part. Okay, let's do this. Alright, next problem is, it says it's going to reach a fire hose is now aimed 20 meters high, 20-meter high wall, and then at a level ground 40 meters from the base of the wall. And the angle is 15 degrees, so that's 15, you will reach the base of the wall when theta is 15. So what you need to do is, to show this, in fact, that's only 1 mark, use part 1. So if you reach 40 meters from the base when theta is 15, you can use this formula. So this 40, that must be v squared sine 2 theta over g. And when theta is 15, it's equal to 40. Okay, so you write v squared sine 2 times 15 degrees over g. That gives you 40 meters. Okay, and sine 2 times 15 is sine 30 degrees, so you have to find sine 30. So sine 30, which is v squared sine 30 over equal to 40g. And then sine 30 is half, so v squared times half is 40g. Therefore, v squared is 80g. So it's quite easy to prove. And then the next part, you find the Cartesian form because you're going to find the angle. How to find the Cartesian form? Eliminate t. Okay. All right, let's do part 3. We're going to get the Cartesian form. So you make t the subject, x equal to vt cos theta. Make t the subject, so x over v cos theta. Okay, like that. And then substitute that into y. Y equal vt sine theta. Vt sine theta. Sine theta minus half gt squared. And then you substitute that in both. Okay, substitute into both. And you get v times x over v cos theta sine theta minus half g x over v cos theta squared. And then the v get cancelled, you end up getting tan. So write tan theta x. Right, that gives you the first term. The second term you don't get yet, so you get gx squared over 2v squared cos squared theta. And then we can change it to 1 over cos squared theta is sec squared theta. So gx squared over 2v squared sec squared theta. Now the question doesn't have v squared. The reason why is they know v squared is 80g. That's from part 1. We can substitute that in here. Substitute 80g in, you will end up getting x tan theta, so y equal to x tan theta minus gx squared sec squared theta over, replace v squared by 80g times by 2. And that g cancel with this g. So you end up getting equals to x tan theta minus x squared sec squared theta over 160 as expected in the question. Okay, good. All right, so we're now going to find out what angle would it be if it clears the wall. So you have to clear the wall. So we have to use this Cartesian equation. So if it clears the wall, you must pass through this point there, which is 40, 20. So if you substitute 40, 20 into x and y, and you should be able to simplify to the other equation. Okay, have a try. Okay, have a try. So substitute 40 into x, y as 20. Yep. There. Yeah. Continue. So we're going to substitute 40 into x, so you get 20 equal to 40 tan theta minus 40 again square sec square theta over 160. So if you simplify that, it should give you this equation. Okay, all right, let's do that. So 40 square, you get 1,600. When it's cancelled, you get 10. So use your calculator. Divide both sides by 10, which you will get, and you get 2 equal to 4 tan theta minus sec square theta. Right? Now sec square theta is 1 plus tan square theta. And if you move around, you should be able to get the correct answer. So you move it to the left side. So you get 2 plus 1 plus tan square theta minus 4 tan theta equal to 0. And you get tan square theta minus 4 tan theta plus 3. Alright. So you get that. Okay, have a read. Alright, good. Alright, once you get this, we're going to do the last part. Find the angle theta for which you will hit the front of the wall. Okay, so what you do is, to answer this question, we're going to solve this equation. So that's a quadratic equation. You can factorize tan theta minus 3, tan theta minus 1. So therefore, tan theta equal to 3, tan theta equal to 1, theta equal to 45. The other one, you use your calculator. So you go shift tan, make sure you do it in degree mode, 71.5 degrees, 71.6 degrees. Alright, so these are the two angles when you will hit the top of the wall. Okay, so let's draw them. So one's at 45 degrees, you will hit the top, 45 degrees. The other angle is 71 degrees. Right? 71.6 degrees. Okay, good. So what angle would it actually hit the front of the wall? So therefore, let's draw the other path. Let me think for a while. Now remember, when it's 15 degrees, you will hit the bottom. Right? That's when theta is 15 degrees. So that means any angle between 15 and 45, you will start to hit the wall, right? Yes? So basically the range will increase. That's the furthest range, right? You will hit the wall. So that means you will hit the wall is theta between 15 and 45 degrees. But there's other range you will hit the wall. Because after a while, after you reach 45, the range gets smaller, right? You will hit like this, right? And then eventually, you will start to, eventually you hit this bit, right? Actually, let's go get rid of this. Okay, so it gets higher, but then smaller range, higher still, and then it gets higher, but then start to hit the top again. And then what happens if you increase more than 71? You start to hit the wall, right? Yes? So therefore, theta has to be between more than 71 degrees, right? 71.6 degrees. 71.6 degrees. But be careful, you can't go too high because eventually you start to hit the bottom again. What angle would it hit the bottom? What angle? So if I go too high, you start to hit the bottom. You won't hit the wall. And then if you go higher, you start to hit this point. What angle would it hit exactly at the bottom of the wall? No, 90 will just go up vertically. Yes, it's complementary. Remember that rule we learned before about, let's make this, remember this one where we spoke about a few lessons ago. Now this part. So if you go to this part, we prove that for them to have the same range, they must have complementary to each other. Okay, remember this rule? So we're going to go back to this page. So therefore, you will hit the bottom again at 15 degrees. So you go 90 minus 15, just like the 15 here, you get 75 degrees. So these are the two possible angles it will hit the wall. Yep. They must have returned the ruler. Okay, all right, good. Okay, let's, I think that's done. Okay, thank you. That's it, yep, thanks. Okay, all right. We've got one more HSC to go through, but maybe I'll get you to have a try. This is a very hard question. So have a try. It's in 2008. There's 2 pages, so try that by yourself. We'll go through next lesson. And then we have some extra questions if you want to try. I wrote down some. Yeah, I know. I can't. Okay, now at the bottom it just tells you there's more challenging questions. So if you want to find some more challenging question, I gave you the year at the bottom. So these are more challenging questions, etc. Okay? All right, good. So I will go back to the last page because you may missed out what I wrote. I'll leave it on for a while. Okay, good. So you can do the chapter review to the